My name is Camila Zamora, and this is my Physics 2211 Lab 3 report on black holes. So a quick overview of this lab is that in the first part, we tested to find the mass of a black hole with the trajectory of a planet going around it. And a quick overview of my results is that the mass of my black hole from part 1 was equal to 8.42 times 10 to the 33 kilograms. And the system in this case for part 1 was the star, and the surrounding was the black hole. For the second part, this included finding the velocity of a ship trying to leave the planetary system of a planet and a black hole together. And a quick overview of my results is that the velocity of the ship was 5.6 times 10 to the 6 meters per second in the x direction, and 8 times 10 to the 6 meters per second in the y direction. For part 2, the system was the ship, and the surrounding was identified as a planet and the black hole. A few important concepts for this lab would be Newton's second law, along with the velocity and position update formulas to calculate how the planets and the ship were moving in both parts of the lab. Then we have the law of gravitation, which is a force acting upon both of these systems, shown by the second formula in the middle, and how we describe the net force and the rate of change of momentum in a circular motion, along with the parallel component of an object's motion and the perpendicular component of an object motion that will both add up to the net force. So here's my code for part 1 of the lab, where I set delta t equal to the amount of seconds in a day. On the left is the rest of my code, where I use the rate of change of momentum and both its parallel and perpendicular components to find the net force acting on the planet, from which we can find the mass of the black hole using the universal law of gravitation. And here are my results for part 1, where you can see that the magnitude of the net force is 7.6 times 10 to the 28 newtons, and the perpendicular component of the net force is 2.34 times 10 to the 28 newtons. And finally, the perpendicular component for the net force is 7.25 times 10 to the 28 newtons. And finally, the mass of the black hole, the average of all the iterations would be 8.42 times 10 to the 33 kilograms. So now we'll go into part 2. Here's part 2 of my code, where on the left we can see all the calculations made to find the net force on the planet and use the position update formula and the velocity update formula to make the planet move. And then I did the same thing for the ship, and then with trial and error I was able to find a velocity that would make the ship not crash into the planet. And this velocity is an x component of 5.6 times 10 to the 6 meters per second, and a y component of 8 times 10 to the 6 meters per second. So here are my results for part 2 of the lab, where the velocity of the ship, as I said before, was 5.6 to the times 10 to the 6 meters per second, and the x component is 8 times 10 to the 6 meters per second in the y component. And as you can see from the calculations, the ship did not crash into the planet or get sucked into the black hole, so it ended up at 2.3 to the times 10 to the 10 meters away from the event horizon. So what does that mean? That we're asked to discuss the net force and its parallel perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. So the thing is that they're both nearly the same thing, where the net force is equal to the rate of change of momentum, and their perpendicular and parallel components are the same. The difference is in how both of these different concepts are perceived. For instance, the force is thought more of as pushes and pulls, while the rate of change of momentum is thought more as change in motion. So they're both going to have the same perpendicular and parallel components. So for the what if part is, what initial velocity would your spaceship need to have in order to enter some kind of orbit around the black hole? So for an object to be in orbit around another object, essentially the velocity of that object would have to be equal to the square root of the gravitational constant times, in this case, the mass of the black hole over r, where r is the radius of the orbit. And is any radius larger than the radius of the black hole itself? So a velocity that worked for me personally was the velocity of negative 7.4 meters per second in the x direction and 4.23 meters per second in the y direction.